Today's lesson is on chemical bonding, and this is the beginning of chapter 7 and 8. Um, Back in chapter 5, 6, we discussed the concept of electronegativity. So I want to just remind you of that, and then let's talk about how electronegativity plays a role in chemical bonding. Electronegativity is the ability of an atom to attract electrons or pull electrons to itself when it's bonded to another atom. And we just finished up our chapter on electron configurations, and we talked about the valence electrons in particular and how to find those valence electrons. Remember, those are the electrons that are directly involved in chemical bonding. And in today's lesson, we're going to look at the difference between ionic bonding and covalent bonding. We're going to take a second to look at a little video that explains electronegativity.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end. Attract electrons toward.
Okay, so in that animation, you saw that with your ionic bonds, the electrons, the valence electrons get completely removed from the metal and are given to the nonmetal. And in the two types of covalent bonds, in one case, the electrons are shared evenly, and then in the other case, the electrons are shared unevenly. And that's one thing we're going to be looking at in this chapter. All right, so before we look at the specific definitions of the types of these bonding bonds that occur, let's look at and compare and contrast the ionic compounds with a molecular compound, the compounds that contain these types of bonds. Ionic compounds consist of a metal and a nonmetal. Remember that from chapter 9. Whereas your molecular compounds, they contain covalent bonds, so they're going to be nonmetal plus a nonmetal. Ionic bonds or ionic compounds, these types of bonds are stronger than the covalent bonds. And so therefore the compounds that contain these bonds are going to have higher melting points and higher boiling points. And specifically their structure is going to be harder. It'll be a harder crystal than those in molecular compounds. Ionic compounds in the molten state, that means that when they're melted, you heat them to their melting point and they melt. Think of molten lava. Or if you dissolve them in water, they will conduct electricity. So we call these types of compounds, substances, electrolytes. When they're dissolved in water, they're conducting electricity. They're called electrolytes. Whereas your molecular compounds are called non-electrolytes. Ionic compounds consist of positive and negative ions that are bound together in a crystalline solid. Your molecular compounds, they can be solids, liquids, or gases at room temperature, and they're going to consist of molecules that can move around independently of one another. So I want to show you a little animation of what would happen if you dissolve an ionic compound in water, and then what would happen if you dissolved a molecular compound in water. All right, I'm going to go to the microscopic level. So here we have some water, and I'm going to just shake a little bit of the sodium chloride in the water. Notice what's happening when as soon as the water comes into contact with the ionic compound, the water pulls the ions apart. So you have free flowing ions here. So if we look at it on an even closer up, more magnified level, if I pull the salt crystal in, notice what happens when I let go of it. The water molecules surround it and literally pulls the sodium and the chlorides apart. This is why ionic compounds are able to conduct electricity. So if we look at it from the macroscopic level, I'm going to pull my conductivity tester over here. If I shake a little bit of salt, look what happens to the light bulb. The more salt I shake in there, as the ions concentration gets greater and greater, the light glows brighter and brighter. These are electrolytes. Now, if we contrast that with what happens with um, sugar, for example. So let's look at a molecular compound. So I'll pull the sugar in. Notice the sugar is a great big molecule, C12H22O11. So notice the water does pull the two sugars apart, but it doesn't pull it apart into ions, so the molecule remains intact and can move around independently. So if we come back and look at the macroscopic level, if we were to put sugar in here and look at our conductivity tester, you can shake all the sugar in here you want to, but the light bulb is never going to glow. It's a non-electrolyte. There's no ions in solution. All right, so let's pick back up here with what we just said. Okay. All right, so the next slide is going to talk about the chemical bonds themselves. So chemical bonds, which is the focus of this chapter, is the force or energy that holds atoms together. Now, there is one underlying theme that you're going to find in all of bonding, and that is no matter what type of bond you're talking about, the elements are trying to get stable and they're trying to attain a noble gas electron configuration. Now, with an ionic bond, you were given an electronegativity table in class, and we'll actually look in another lesson at how to calculate this. But this triangle means the difference in or the change in, and here's our symbol for electronegativity. So this is called the electronegativity difference. If it's an ionic bond, when you subtract the electronegativity values of the atoms involved, you're going to get a difference of 1.7 or higher. That's how you will know it's ionic if you use your electronegativity table. Remember, with ionic bonds, you have a metal plus a nonmetal. And in an ionic bond, the electrons are transferred from the metal to the nonmetal. So if you take a look at the electron configuration, for example, for the sodium atom, 1s2, 2s2, 2p6, 3s1, this is the highest occupied energy level for sodium. Notice there's one electron here in the s orbital. For chlorine, if you look at his electron configuration and look at the highest occupied energy level, notice in the p orbital there's only 5 electrons. So we learned in the last chapter that the orbitals want to be either full or half full to become most stable. So what happens in an ionic bond is this valence electron from sodium is transferred to the 3p orbital of the chlorine. And what happens is it gives the sodium a full valence shell, 2s2, 2p6, and now the p orbital has 6 in it for chlorine, which forms the chloride ion. So they both have an octet in their valence shell, which stabilizes the atoms. Now with covalent bonds, these are going to be found in molecular compounds, and there's two types of covalent bonds, nonpolar covalent and polar covalent. Let's first look at the nonpolar covalent. You have a nonmetal and a nonmetal, and these share electrons equally, 50-50. The electronegativity difference between the atoms involved in this type of bonding is going to be anywhere between 0 and 0.4. So there's going to be very little difference in their electronegativities or their strength of pull on the electrons. Usually they're the same atoms, your halogen Huns, your diatomic molecules. I always think of nonpolar covalent. Think of the terms of like this. If this were the Earth and this represents your equator and your North and your South Pole, if this represents, the North Pole represents one atom and the South Pole represents another atom, if they're sharing evenly, they're going to share exactly on the equator 50-50. So nobody pulls any harder than the other. So this happens like with diatomic fluorine. They're going to share their electrons. It's covalent. Now, the second type of covalent bond is a polar covalent bond. These also happen between nonmetals, but the difference here is they share their electrons unequally. There's an uneven pairing of the electronegativities with the atoms. Their difference in electronegativities is going to be in the range of 0.5 to 1.6. That's sort of a mid-range. So going back to our example of the equator,